I am Shanaz. In this lecture, we are going to study some operations on ideals. Suppose, let us first define what do we mean by a sum of two ideals. So, this is the definition of the sum. So, let us consider two ideals. So, let I and J be two ideals in a ring A. So A is our ring. Then the sum of I and J so this is actually an ideal which contain elements of the form x plus y, while this x is in I and y is in J. So this is an ideal, and not only ideal but it is the smallest ideal which contain both A and I and J. So let us make this remark here. So I plus J is the smallest ideal which contain both I as well as J. So we can generalize this definition to any family of ideals. So more generally, if say we have a family I, so this be any family, possibly say infinite, possibly infinite. So this is the family of ideals of A. Then the sum so here we write in compact notation sum of I, while the sum runs over I. So this is an ideal which contain the elements. So some of these ideals is actually an ideal which contain elements of this form xi, where xi is in I sub I for all I, and all xi's but finitely many are 0, where all xi's but finitely many are 0. That means in this sum there are only finite number of terms non-zero and the rest of terms are 0. So this is the generalization of this above definition. Now then we have the definition of product of ideals. So this is the another definition. So let say I and J be two ideals in a ring A. then the product then the product of I and j is also an ideal, is the ideal which contain the elements of the form. So I and j consists of the elements of the form xi yi, where this I runs from 1 to n, i.e. this is the finite sum, otherwise this won't make sense if this is infinite sum. So this xi is in I and yi is in j. So this is called the product of ideals. So in particular we we define the product for any finite family of ideals. So similarly we can define the product for any finite family of ideals. Ideals of A. So in particular suppose I is an ideal in A, then we can define the nth power of I. So in particular I to the power ny, this n is some positive integer, is the ideal which is generated by all products, say x1 x2 through xn, where each xi is in I. For all I. So then this is again an ideal and as a convention we write I to the power 0 to be the unital ideal, that is the ideal generated by 1. Now let us take and consider an example. So we have this example here. So let us consider, so let A be the set of integers. Now Z being a principal ideal domain, so each ideal in Z is principal. So let us take two ideals, say I and j in A. So let I let us suppose this ideal is generated by positive integer m, and j an ideal generated by n, be two ideals in A. Note that these m and n are positive, where m and n are positive integers. So then I plus j is, so then I plus j is actually the ideal which consists all linear combinations of m and n. So it consists of mx plus ny, where x and y are integers. Now the least positive integer generated by m and n is their greatest common divisor. So but the smallest possible integer which can be expressed as the Z linear combination of M and N is actually their GCD. So this is the GCD of M and N. Now if GCD of Mn is D, then I plus J will be an ideal generated by D, because this will again be an ideal of Z, and hence I plus J has to be a principal ideal. So that means it will be generated by a single element, and that single element will be the the greatest common divisor of M and N. So then I plus J will be the ideal generated by D, where D is actually the greatest common divisor of M and N. Now if we, so this is the case when we take this sum. So this is the first case, and the second case is, so also if I take the product Ij, so that is the ideal generated by M times the ideal generated by N. So this is actually the ideal generated by M times N, because this M n will be the least integer which is in the product of Ij. I mean the smallest integer container, positive integer contained in Ij will be the product Mn. Again Ig being principal, so it has it will be generated by Mj. Now let us look at their intersection. So and I intersection J will be the ideal generated by M intersection ideal generated by N. So this means so this implies, if say X is in I intersection J, then X is in M as well as in N. That means M divides X and N divides X. Then X is in M implies M divides X, and X is in N implies N divides X. So that means an element X will be in the intersection of these two ideals if X is a common multiple of M and N. So this further implies X is in the intersection of I and J if and only if X is a common multiple of M and N. But again, I intersection J being an ideal of Z, it has to be a principal ideal. So this intersection is going to be generated by a single element. Now we have to look at the smallest positive integer which is contained in Ij. Obviously that will be the least common multiple of M and N, and hence their intersection is generated by the least common multiple. So therefore I intersection J is actually the ideal generated by, say, Q, where this Q is actually the is actually the LCM of A, M and N. Now let us make a remark here. So if we look at the product I and J and their intersection, so one is contained in the other. If we look at this containment, this is trivial. Let us see how. So the containment I J contained in I intersection J is trivial. So let us pick an element in Ij. So let X belongs to Ij. So this implies X is some so X will be like PQ, where P is in I and Q is in J. So this means, but let us consider since PQ is QP, because our ring is given to be commutative. So if we look at the element QP, now Q being an element of the ring A and P being the element of I implies QP is in the I. So but QP, which is equal to PQ, is in I, and similarly now let us consider P to be an element of the ring A and Q to be the element of J. Then PQ is in J. So and PQ is in J. So implies, so this would imply PQ is in the intersection of I and J. That means Ij is contained in I intersection J. So this containment is trivial. But let us see when the reverse containment is true. So suppose I and J is such that their sum is actually the unital ideal, then there exists some element I in I and J in J such that their sum is 1. So then there exists X in I and Y in J such that X plus Y is 1. So now we have to prove, now given this condition, the reverse containment here will be true. So let us pick some element in I intersection J. So let A is in I intersection J. So we can write this A as A. So we can write this A as A times 1, which is same as A times 1 is X plus Y. Since the multiplication is distributive or addition, so this is same as AX plus AY. Now look at this element here. Now A is in I as well as in J. So let us suppose A is the element of J and X. Now this AX is same as XA. Now X being an element of I and A being in the intersection, so this is also an element of J. So this X is in IJ. That means AX is in IJ. Similarly, let us consider AY. Now A being in the intersection, so this A is in I and Y being an element of J. That means this AY is in IJ. That means this is in IJ, this is in IJ, hence their sum is in IJ. So this is in IJ. So therefore the reverse containment is true as well, and hence I and J is actually I intersection J. So one should remember this uh, equality appears here when the sum of these ideals is unital ideals. Such ideals are called the co-prime or the co-maximal ideals. So let us define these ideals. So we have this definition here. So let A be a ring and I and J be ideals in A. Then I and J are called co-prime, or sometimes they are called co-maximal. If the ideal generated by I and J is the unital ideal. So given this condition, one can make an observation. So if I and J are co-prime, then the product is always the intersection. So if we look at the ring of integers, so A is over ring Z. Let us suppose I is the ideal, say ideal generated by 2, and suppose J is ideal generated by 3, then the ideal generated by I and J is actually the ideal generated by their greatest common divisor. So 2 and 3 being relatively prime means there is a linear combination, a Z linear combination such that 2x plus 3y is actually their GCD, which is 1. So this element being in I plus j implies 1 is in I plus j. So this I plus j will be a unital. Now given that this I plus j is 1, that means if I look at the intersection of I and j and their product, that is going to be equal. Now let us look at ij. So this will be the ideal generated by 2 times 3, which is 6. And if I look at the I intersection j, that is going to be an ideal generated by their least common multiple. Now least common multiple of 2 and 3 is 6. So this is the verification. So if I plus j is the unital ideal, I and j are the co-maximal ideals, then these two ideals are going to be equal.